presentation about the generative discriminative basis learning for medical imaging. In the last presentation, we had let's recap what's the problem. Here, the problem is we want to extract some type of the feature. This feature must be meaningful in terms of anatomical information of the body. It must be discriminative. It means if we use these features, we can, for example, have a accurate. We can use these features to have a accurate discrimination, and also these features must have good ability to reconstruct the original image. And we spoke about, for example, matrix X. It was a matrix by dimension D and n number of the sample, and it's as an example, for example, if we have a 3D data of the body, we can extract, for example, box in a small box in this whole data, and reorder it as a column and put it in the, for example, X as one sample, and continue for all of the, for example, possible samples, or anything else that, for example, give us a D dimension and a number of the sample. And we assume that we can decompose this matrix to a matrix B multiple matrix C, which the matrix B was our basis, and C was the loading coefficients, and also the with D matrix, with B matrix multiple to transpose of the X multiple weighting, we can have labels. It means we can use this basis for labeling new data, and we assume that there is a conditional relation between xi, and xi is original data and yi is the label of that, and this one is the weighting function, and bi is our basis, and ci was our loading coefficient for each sample, and we try to maximize the a posteriori map estimation and maximum a posteriori map estimation for the for B, C, and W, where the log probability of B, C, W given the data and labels, and I derived, for example, this part P, B, C, W, X, Y, it was equal to P, X, Y, B, C, W, P, C, D, W, and this part we can have P, C, P, D, P, W, and for this one we have Px given BCW multiple Py given X BCW, and here W and X are independent, and this one is equal to Px BC, and here Y and C are independent, and this one is Y X B W, and also we have P B P C P W, and if we want to log of this function, it's this one log of this one plus this one plus. Okay. Yes. And this one is equal to log of first term Px BCW plus log of Py X BC plus log of PC plus log of PB plus log of
XCW. The second was XCW and the first one is a BC. The first one doesn't have double. The second one is the XCW.
yes. Okay, and here we want to maximize this function, and is yes.
That is not an equal sign trade. You have that. I guess I'm late to point that out, but
Yeah.
this is not equal. Right? It's PCW. Yeah, you can write proportional base.
Yeah, sure. Yeah, it's true. Because there is some normal claim. Yeah, it's proportional. That's true. Yeah. But this one is equal to this one.
Yes.
And this term we call that generative term. This was this was constant. And I explained, for example, the way to decompose of a matrix X to matrix B and C, which is a well-known techniques. That's, for example, PCA, LDA, PCA component principal component analysis, and LDA linear discriminative analysis, and a lot of techniques that I listed. And now I want to continue for example, for finding each term. first, I will start with the generative term. The generative term, the goal of this term is to keep the decomposed matrix, the result of decomposition, as similar as possible to the original data. The second term, the objective of this term is to have a basis and find the W that we can label the data, the available data, and if we have a new data, we can use this information. For the finding the this decomposition, we can have different assumption for the noise based on what's the assumption of the noise. For example, in this paper, they assume the noise is Gaussian noise, and they assume the probability of x given bc is equal to lambda 1 identity matrix, and based on this they derive the generative matrix as minus dot p x given bc, which is equal to lambda 1 divergence term of x and bc, and here they use the lambda 1 for use norm of x minus bc, and as I said, I didn't write it down here, but instead of maximizing this function, we can use the minimize of the minus of each one. Let me write them here. And we use this one as d xbc. This one is all loss function. It's y x b w, and the last one is conversion term, which is rbc and w. And also we have some assumption for the BC, that the B and C function basis, the vectors must have feasible sets. And I will explain more about that and continue. And okay. Also, we had some discussion on the discriminative term. We assume the discriminative term is a likelihood function, and we can assume that we assume the L of y x b w is equal to 1 over number of the sample sigma of y h w of b transpose x, which I raised that if we assume that there, for example, x transpose b multiple w is y, and here the last function is we assume the label is plus or minus 1, and we define this function as 1 minus y w transpose b transpose xi plus a square. It means we assume the maximum of this value if it's for example minus, we assume it's 0, but if it's more than 0 we use the original value. And there is another function like logistic function, and they call this one hinge function for the label.
What was the HW?
HW is it's W B transpose X. For example, HW of A is WA. Yeah, it's inner product. Yes.
X is approximately BC or B transpose C. I forgot.
BC.
X is BC. Yeah. X BC.
So why do Y is modeled that way? I mean, I don't quite understand why. I think B are the basis, right?
Yeah, B are the basis.
Yeah, B are the basis. Then I felt like X transpose B, it should be something approximately equal to C. So then that would make sense, right? But then I would think like then the X should be approximately B transpose C instead of.
Okay, X is BC, and if I multiple X transpose here, it's I equal to X transpose BC. You mean it must be X B transpose?
I don't know. I mean, I would guess like X transpose B is approximately equal to C. I felt like that's the reason why you have like X transpose BW is approximately Y. Because C are the coefficients, right? So I probably I'm trying to estimate Y as CW, something like that, like C as coefficients. And then So I would follow X transpose B transpose, for example. Let's see.
X transpose, B transpose. Really?
Oh, wait. Maybe you're right. I guess it's okay.
Because the
Oh, okay. I guess it's right. It's right.
B
Yes.
also
Yes.
reduce the dimension of xt.
Oh, okay. I guess it's all right. So you have like X is approximately BC, then B transpose X is approximately equal to C, because B you can't assume it's unitary, I guess.
Yeah.
So then like you have C transpose is X transpose B. So I guess everything all right.
And they defined two sparsity here for the medical, for example, needs. And they have they use two terms for sparsity: box sparsity and group sparsity. The group sparsity, the purpose of group sparsity is, for example, if you have a basis and you want to reconstruct the image, you it's interest in this kind of decomposition that your basis describes something meaningful. It means if you have a basis that's, for example, they must be connected. For example, you don't want to have something like, for example, average, because average is for over all of the data. And you need something specified in the, for example, location, the basis that describe the spatial location in the data. And they use group sparsity to keep the bases, I can say, for example, dense in some area. They use the information, for example, like segmentation of the image, and they force the bases to be dense in some area, and the rest was, for example, equal to 0. It's somehow it's maybe extra force to have a meaningful decomposed basis, as you know, in the non-negative matrix non-negative matrix decomposition, factorization, NMF, non-negative matrix factorization. The basis is, it has some meaning. For example, if there is the image of the face, each part of the decomposed basis has some meaning. And here they use the box sparsity and group sparsity. Let's define each of them and then more explain about what is the effect of the box sparsity and group sparsity on the decomposition. They define original definition of box sparsity is, for example, have the coefficient of B here either 0 or 1 and only 2 values, and the number of the non-zero coefficient in each column less than, for example, one threshold. If I want to write it down, it's for example, bj bj is a whole column. Okay, it's 0 or 1 power d because we have a d dimension, and the norm of 0 norm of bj is less than equal lambda. Really, it's we have two types of the bases. First one, they are only 0 or 1, and we don't have any constant in the number of the 0 or 1. And the second type, or the other type, is bj. It can be, for example, any number, but the number of non-zero coefficients must be less than lambda. It means we have two types of the bases. First one, they are 0 or 1, but in the second one, if there is something between, the number of coefficient must be, for example, certain limit. And we cannot use the, for example, the ordinary sparsity, because by using b, we originally reduce the number of the dimensions from the, for example, d dimension in the original data to a dimension less than that. It's, for example, k, which k is less than d, and maybe there is no sparsity in general, but we can define some sparsity like this into the data into new space.
Excuse me, but how we can find the lambda?
You must you mean this one?
Yeah.
For you must assume, or you must define the lambda. For example, lambda is not your variable. It's a constant number that before starting the optimization, you must define. For example, you need some number of the coefficient, and there is some experiment in this paper to, for example, how to choose this lambda and what's the effect of this lambda, because we have a I think three lambdas here. This one is for force the bases that they show the for example certain number of the non-zero and the rest was 0, because we don't want to, for example, I explained in the before session, for example, in the PCA, when we try to decompose the matrix, we have the some bases that it's spread all of them. For example, if you have 2D image, it's spread all of the image, and for example, it's something between minus infinity and plus infinity, something between. And but here we need to keep the number of the zeros in the, for example, in the number of non-zeros in the some ratio between the number of zeros and number of non-zeros to, for example, create the basis that it's dense in the, for example, some meaningful part of the body.
What else? This is the set for BJ. What you written down here?
This one BJ is column of the B.
Yeah, but I mean, like the first set is doesn't say like it can only take 0 and 1 for the components of BJ. Is that you say like BJ is in the 0, 1 RD, so it can only be 0 and 1?
Yes.
Then
for example, we have two type of the BJ. One of them, if it's 0 and 1, it's okay. You can have any number of the 0 or 1.
Oh, okay. You mean union, that there's intersection. The two sets is a union.
Is or and.
No, I think it's and.
Why? It doesn't make sense.
Because, for example, if we have some places that it has a lot of 1, again, we didn't apply the box sparsity. Because in the box sparsity, for example, if we have a 2D bases, if, for example, I select one of them and reorder it in the original way, I want to, for example, have the basis that it's, for example, dense in some area and the rest is equal to 0. And if I have a 0 and 1 in, for example, in non-limited number of the 0 and 1, again, I will have the problem with, for example, some spreading in the all of the bases. And for example, if I have, for example, if it's a dense base, and if I have, for example, something like this, again, I cannot, this type of the basis is not anatomically informative. We want to have something that it's matched to the anatomy of the body. And if we have something like this, it's not acceptable.
What's BJ here? When the dimension is D, you mean the image have D pixels, right? Is that what you mean?
Yeah, image is D pixels.
D pixels.
Yeah.
And then like,
yeah.
When you say and, it doesn't make sense, because then you cannot. I mean, the second condition doesn't have anything to do, like the second condition, or like because you already forced it can only be 0 or 1. Then in the second set it will be only 0 and 1 anyway, right? Why is like RD there?
Maybe it's a union.
No, it's not union. This one is true because.
But then the other ones are not RD, right? Or like it doesn't matter, I guess. But it just sounds weird. But RD is just 0 and 1, right? Also.
They call it this one as a sparse indicator and this one as a.
But you cannot have it at the same time. You can put a union there. It's fine with me, but you can't end there. Just it can't happen at the same time.
I need to again review the material, and in the paper it's this one, and I'm thinking this one is true, but I have problem with this one and why this one is R. And I need to.
I guess it can be typo and stuff like that. It happens often.
In the paper they emphasize in this part and said this one is sparse. It must be sparse. And if the number of 0, 1 it was, for example, infinite, I think maybe. Yeah, I need to.
So you mean it cannot be the whole thing is all 1?
Yeah.
Something like that.
Yeah, they said it can be. It can't be.
It cannot be.
Yeah. And because of this, I need to read the material and.
Okay.
Maybe that
But the
sign
problem
has
is
another
like,
meaning.
yeah, but the problem is that you have to end then it means that like you cannot have your basis is not 0 and 1.
They add this one because you cannot,
Yeah,
for
but
example,
once
do
you put
everything.
the and there, your basis cannot be like non-0 and 1. You cannot have basis of 0.5 or something like that.
But really, this is the definition, and after
I mean, I think I will put it all there, and then at the beginning also put the condition that like you cannot have the. I mean, I can have the 0 norm condition in the first step.
I think they thinking about this problem and change it somehow. For example, they said finding this one and this one together is hard, and because of this they changed the assumption. And
Maybe that sign has a just define that
No,
sign. as
no,
something
no,
that
no,
you
no, no.
say.
You cannot define a sign.
No,
It doesn't make any
yeah.
sense. It's worse. You cannot just.
But I think they try to mix these two together.
No, I think it's a typo.
As a
Yeah, and somehow they said, for example, because the finding that the zero norm of this one is hard, or we can do something similar to this to finding this one, and they change, for example, the whole thing because of, for example, instead of using B0 less than lambda, they change it to with this sign means they relax the they relax the they use the relaxation on that and say, for example, this one can be known 1, and also for this part, instead of using Bj in the 0 and 1 only, they use the B can be between 1 and 0, and
He has a big. Oh yeah.
B.
BJ.
Yeah, this one is B. It's and they said, for example, B is bigger than, it's equivalent to B bigger than 0, and the norm infinity of B less than 1.
I guess you want to be careful with your B here. Like sometimes you write it as a vector, and then like this is approximate. Okay, that's.
Yeah, I think this one is better. Because it's speaking about one column.
One column, yeah.
Yeah, we want to have only one column. Everything is about one column. Okay. And for example, B, I said is B 1 to B K, and each B I R D, and K D. And Bj infinity is less than 1. It means
BJ is equal. Yeah, between the 0 and 1. You mean all of the coefficient of this vector is between the 0 and 1.
yeah, they, for example, use this relaxation, and instead of using either 0 or 1, they use something between 0 and 1. This assumption was for box sparsity to control the number of the coefficient vector, and they use the group sparsity. In the group sparsity, if I want to, for example, explain what for example, if we have some segmentation in the image, and for example 1, 2, 3. For example, here, these are boxes, and they define a function, they define an operator. I can say, for example, this is an operator, which is B, if I got this one, G1 and G2 and G3. For example, I have some image and I segment it into 3 segments, and B of G1 and this one is one of my BJs. B, let me call it B instead of BJ. And B here is equal to, for example, I wanna use it as, for example, 1, 2, 3, 4, 5, 6. Okay, this one is one of my columns. And B, this sign G1 they define. This is, for example, 1, 2, 3, 4, and 0, 0, 0. For example, the coefficient that's they are in the, for example, this segment, they are equal to, for example, these values. This is the value of the means the value of the one, not the font. Okay. The value of these pixels are in the B, but the rest are equal to 0. And they define the group sparsity by, for example, over B 1, 2 is equal to sigma of rho G. G is belong to a big set of the G, that all of this segment are in the big G, and rho of G is the number of member in the G 1 over the number of the member of G. For example, rho of Gi is equal to 1 over Gi. This is the number of member in the G. this one is this sign. Norm 2 of this. And also they define the b infinity and 2 is equal to maximum over g rho g they use box sparsity and group sparsity to apply on the columns of B to keep the three properties that I again want to review that. First, it must be meaningful based on the anatomical information. Second, it must be discriminative. And third one, it must be generalized for the new incoming samples. And they started their optimization over this objective function to find the minimum of lambda 1 dx dc plus lambda 2 loss function of y b x w plus norm 2 of and find b c w. Okay, and here b it must here b must satisfy box sparsity or group sparsity, and I put here the lambda 3. For example, the meaning of the lambda is the box sparsity or group sparsity. It's some code based. And also the loading coefficient must be this is the matrix and this is the matrix. And for example, the meaning is all of the coefficient in the C must be bigger than 0. And they have lambda 1, lambda 2, and lambda 3. And for example, if we have one set of input data, we can change the parameters lambda 2, lambda 1 to, for example, increase the effect of the generative term or the effect of the discriminative term, or for example, applying the box sparsity and group sparsity on that. And in the experimental result, which I will explain it with some slides in the next session, with some brief introduction, not introduction, explanation about how to apply the optimization. In the next session, they have some experiment on the, for example, the value of lambda 1, lambda 2, the, for example, the value of lambda in the box sparsity, or in the number of the, for example, applying the group sparsity in the bases, and they got different results on the different problems. For example, in the brain, they find the bases that it matched to the, for example, the specific part of the brain, and based on that, they, for example, they use this one to labeling the, for example, each part, and find, for example, abnormalities in the brain, and something else that I will explain in the class. If you have any question, anything else?
Do you have any questions?